All right, so the second thing we're going to look at here is collisions and efficiency. Now, the idea is when you have two objects, it's possible for them to hit one another. And them hitting one another mediates all sorts of things, such as chemical reactions, whether or not, systems form larger structures, the whole bit. Now, the idea behind collisions is if there's no external forces coming in, momentum is always conserved before and after the collision takes place. Now, uh, momentum may be conserved, but it's possible for a collision to occur in which momentum is conserved and energy is not conserved. In other words, energy can be lost to some kind of internal or alternative type of energy. And this is what actually differentiates the two principal types of collisions. Although momentum is conserved in each, if energy is conserved, we say that this type of collision is an elastic collision. And if it's not conserved, we say it's an inelastic collision. So that's the first thing we're going to look at. The second thing we're going to look at is efficiency, which deals with how much of our energy is converted from one type to another. But we'll start with the collision. So the idea here is we have two 1 kilogram masses that hit one another. Initially, one is moving at 2 meters per second to the right, and the other is stationary. Afterwards, they stick together. And for this, you want to figure out the type of collision. In order to do so, you need to check to see if energy is conserved or not conserved. As we're only dealing with things moving, we're only going to deal with kinetic energies. However, to do so, we need to know the velocities of everything both before and after the collision. So for this, we're going to use conservation of momentum. So what we're going to want to do here is we're going to want to take a look at our momentums. And if you recall, momentum is mass multiplied by velocity and is a vector quantity. And what we're going to do is we're going to take a look at our system. Our total momentums are going to have to stay the same both before and after. So what we're going to do is we're going to take a look at our system before the collision takes place. Now, before the collision takes place, we actually know both the velocities. Before the collision takes place, I know the velocity of one of the 1 kilogram masses. I know it is 2 meters per second to the right. All right, so we're going to put it in a Cartesian form, working in base SI units, so we'll omit the units for now. And for the second one, I know that it is stationary. Right, so you can say it's equal to 0, and that just means it's 0 in both directions. Now, with this, I can actually find the momentums of each. All I need to do is take these vector velocities and multiply them by the masses. In this case, the masses of each are just 1 kilogram. So in base SI units, my first momentum will not change numerically, but it will change in terms of the units. Right? It'll be in kilograms meters per second because we're just multiplying it by 1 kilogram. And for the second one, my momentum here will just be 0. And you can put the units in or not, it doesn't really matter. Now, the idea behind the collision system is the individual momentums can change, but the total momentum can't. So if we want to find the total momentum here, so you can use total or net, we're going to add them together as vectors. Now, the whole reason we did this is because when we're dealing with our collisions, we're going to want to compare both before and after they collide. This total momentum that we found down here at the bottom, it's going to be the same both before and after. Now, afterwards, you're told a couple of things. The most important thing you're told is that they stick together. That was really, really thin. They stick together. Now, when things stick together, they move as one object. That means they're going to have effectively one mass and one velocity. So when we're dealing with this, we're going to treat them as being stuck together. So here we're going to have a mass of 1 plus 2, because we're going to treat them as a single object. Now, if they're stuck together, they were both originally 1 kilogram. Together, they're going to be 2 kilograms. Right? And this is also the total mass of our system. Given that this is the only thing that's present in our after system, because we're going to look at it as one object, my total momentum must equal to the mass of the only object I have multiplied by its velocity. Again, if they're stuck together, you can treat them as if they're one thing. Now, with this being said, I can solve for this new total velocity. There we go. Sorry, I hit the wrong button on my keyboard. So all we need to do here is take the total momentum and divide it by our 2 kilogram mass. And we'll get 1 meter per second to the right. Now, with this being said, this is the conservation of momentum type that's always true. Now, what we want to do is we want to figure out the type of collision that we have present. To do so, what we want to compare is we want to compare the total kinetic energy both before and after the collision. Now, we can do this fairly quickly because we do know how to take our speeds and our velocities here and use them to determine the total kinetic energy. So if we take a look at the total kinetic energy before, we have 2 objects here. The first object will have a kinetic energy of 1/2 multiplied by its mass multiplied by its speed squared. Right, so the magnitude of its velocity, and since it's going straight to the right, it'll just be 2. And for the second one, the second object that's stationary in the before case, well, it's not going anywhere. So right away we can say that it just won't have any kinetic energy. So doing this, we can actually calculate the total amount of kinetic energy in joules that we need. And here, if you calculate it out, we'll get 2 joules. We can also take a look at the total kinetic energy after. And now, afterwards, we are treating this all as if it's one object, so we're going to have 0.5 times mv squared. Here, we're going to treat the mass as 2, because it's the total mass. And here we have our speed, or the magnitude of our velocity, just being 1, because the magnitude of velocity is just 1 meter per second to the right. Likewise, we can calculate this out, and then we'll get 1 joule. So what you'll notice here is, even though my total momentum is the same before and after, my total kinetic energy is not. Right? I've actually lost kinetic energy. I've gone from having 2 joules to 1 joule. Now, in terms of the type of collision, this here is an inelastic collision. Inelastic literally means energy is not conserved throughout the collision. Elastic means kinetic energy is conserved throughout the collision. So just by comparing these two, right, so all you need to do is just check these two. You can say right away that this is inelastic. You don't need to worry about the momentum because it's always conserved. And that's the first thing that we're looking at. For all collisions, this is pretty much how it goes through. If you're sitting in the lab, there is a lab that deals with collisions. Every collision you do in the lab is inelastic because, there's friction and sound loss and everything else. All right, so this is part 1. Now, I'm going to get rid of this because for part 2, we only need these. In part 2, you're asked for the efficiency of this system at converting initial kinetic energy, or the total kinetic energy you have before, to final kinetic energy, or the total kinetic energy you have afterwards. Now, for efficiency, you can calculate it. It uses the Greek letter eta here. It looks kind of like a funky N. But the idea is what efficiency does is it compares the output you consider useful to the amount of energy you had to put in order to get that output energy, or that output change in energy. You can use this with energies, you can use this with powers, right? The delta here just indicates that you're looking at some type of energy, right? Or you're picking up some type of energy. Now, if you take a look at this, we're converting initial kinetic energy to final kinetic energy. So if our goal is to find eta here, we're just going to simply want to divide what we consider to be the useful output by what we put in. Now, if we're converting initial kinetic energy to final kinetic energy, whoops, that's the wrong one. Got myself mixed up here. If we're converting initial kinetic energy to final kinetic energy, our input is what we start with, and our output is what we end up with. Now, with this being said, you can divide these. You'll get 0.5. Now, 0.5 here is the proper efficiency, the one you're going to want to use in math. Some people like to convert this to a percentage, which is 50%. And if you think about the numbers that's used, that does make a good deal of sense. We went from having 2 joules to 1 joule, so we lost about half of it, or we retained about half of that which we started with. And that, typically speaking, represents an efficiency of 50%.